So okay, like we talked about like optical flow last time, so I just let's review a little bit like what we talked about last time. So remember that optical flow is basically just like trying to track the apparent motions like in your video or image if you have like a pair of images. So from one image is to another image, like how each pixel like moved like from one to another. And or typically it can be like two separate frames or like two consecutive, I should say consecutive frames in a video stream. So there are several key assumptions there, like we have this brightness constancy. So it's like the pixels in one frame is not going to change right, in terms of intensity a lot to the with respect to the other frame. And also we assume the motion is small, like it may have like tiny motion. Like I didn't even draw any motion. Maybe like it move a little bit, but it's only a little bit. And also like some spatial I think you can redo the yeah you can redo but you probably need to fill in everything again, so be be sure that you yeah fill in like everything. Yeah, I um yeah, if you don't fill in everything I guess probably it's fine. Yeah, better you fill in everything. Yes. Okay, so let's get back to here. So we mentioned these two assumptions, also like the assumption for spatial coherence. So it's like if you consider there's an object like correspond, like basically the point is on the object, then like every points in that object will moving in the same directions, right? So that would be like the points nearby most likely with high probability that like will be moving coherently. So and based on this Byteless constancy condition, so we let's say if we have this U and V are the uh, motion field, and UXY, VXY is basically the motion, the X and Y direction motion at the pixel X and Y. Then in the next frame, that basically frame T here, like from minus 1 to T, then I should have this simple equations here, right? Simple equation that like in the next frame, I shifted by UXY and VXY should be equal to the previous frame at X and Y. And using Taylor series expansion on this one, then I have this guy here. And then if I subtract that, basically these two are equal. So therefore the difference should be equal to 0. So I should have something like that, like or like if just in a vector form or gradient form would be just like this. So but this is like this is the important equation for the brightness constancy equation. Um, but for the brightness constancy condition, and basically all these optical flow algorithms are kind of derived from this one. So we mentioned several algorithms for optical flow. The simplest one is the Lucas Canada. That basically just like because if we think of this equation here, let's say if I have an image like we mentioned that last time, if I have an image like maybe 10,000 pixels here, like 100 by 100, then for each of the pixel we have an unknown u and v here, right? So therefore like you'll be like actually 20,000 variables here, but here like for each of the pixel we only have one equation, so therefore we have much more, basically double the number of unknowns than the number of equations. So uh, so therefore it's actually in general it's a ill-posed problem. And so I would just use some of you guys. Okay, for some reason I cannot mute. I don't know why. So anyway, um, so for Lucas candidate, what uh what we assume here is that we just take a small windows and we assume that all U and V are the same. So for example, if I take a window of 5 by 5, then I will have 25 equations per pixel, basically. Um, then of course, in this case, I only have two unknowns, I have 25 equations, I can solve that. Again, it's like some least square problem, we can be solved very easily. Or we can have this Han I don't know how to pronounce that honestly. Hartshorne method is just instead of like taking the entire window to have same U and V, we just put a constraint here or like a penalty here so that U and V doesn't change too quickly. So this is again like some very typical way, typical engineering approach, right? You add a regularizer to your optimization problem, and then you're trying to kind of minimize the total uh, uh, total this value here, because this value is supposed to be zero. We just sum square all of this, like so trying to minimize that added with this additional constraint here. And as we talked about last time, this is a typical Euler-Lagrange problem. So with the Euler-Lagrange equation, then we have this one here and substitute the partial derivative. We have equations like this. And then like for the Laplacian here, Laplacian operator here, we can approximate as like the average multiplied by the average of the pixel, like with the neighborhood, sorry, not multiply, subtracted by um, the center pixel center value. So then we can substitute this into here, and then like we arrange the term, then finally we have like iterative uh, kind of update for UMV as this one here. And this is the Hornstrong method. And we also mentioned the Gunnar-Fallenberg that basically is take a quite different approach. Of course, it's also need to satisfy the brightness constancy condition. So, but here, like we also added an additional assumption that like the image can be uh, kind of like fitted like using a quadratic model. So therefore, like for both images, we fit it quadratically. So with this one, like with A and B here, and the A and B here, right? So here we assume the A to be the same, but you don't need to make the A the same actually. Maybe I put A1 and A2 here. After you fitting that, so then like you should have, uh, okay, yeah. First of all, I should say like, because one of the images the shifted like version of the other one, right? So we'll have just say like the first one shifted by D will be equal to this one, but both of them can be fitted like quadratically. So therefore, like for the second one, if I expand the quadratic function here, so I should have the B2 will be equal to this guy here. And so therefore we can simply find the shift here, D is just equal to this guy, simply. And for the A here, like we can just take the average of A1 and A2. So um, very simple approach. And then like we can, for this one here, typically like we will kind of use a windows like in the uh, uh, Lucas Canada case, that like we'll just take a window, but these windows we can make it more smoothly. Like in the Canada's case, like we just take a kind of like kind of, what should I say, like a uh, hard window, I will call it, like in the sense like you just have like everything inside the window is like you can think of as a weight of one, everything outside is zero. But here we can take a smooth window somehow, and of course you can do that for the Canada as well. So and then like, if you substitute all this, then the D update will be replaced by this guy here, and we can also make it like iteratively uh, that we mentioned last time. So basically, it's like if you have already like a pi approximation, pi estimate of d, then you can like put that into the equation as well in the update. So therefore, like you have a each time you kind of have an iterative improvement of the estimate. Finally, like this often that like in the actual algorithm, they also restrict the displacement kind of expression. So they will assume like the displacement maybe like take a polynomial expression, for example, like this. Then if you do that, then like your D here will only restrict by certain kind of polynomial expression. And you need to change this appropriately. But of course, most of the time, like um, you don't need to actually implement this. Yeah, because for example, like for the Ghana final back, that one so it's already like implemented in OpenCV, but it's good to know like a little bit of this detail, so therefore you know like what the parameters mean. For example, in the parameter it mentioned about the polynomial is actually for this one here. So okay, let me this is a little bit uh kind of a review of last time. So let me continue with the slides. Let's see. Uh, so okay, one thing like remember like in these assumptions here, we have this like small motion assumption, right? But for example, like you have like images like two frame here, like one frame and the other frame, like for pixels like in the far away scene like here, like for example in the house, maybe the motion is kind of small, but like for the tree, like more kind of closer to the camera, the motion will be pretty big. So maybe like this is like this may violate this small motion assumption there. So one way to kind of like fix this is like we can simply do a kind of that's actually already like technique we mentioned in the past is that we can do a pyramid uh, kind of like decrease the resolution somehow. So in a lower resolution, then like if you kind of look at the lower resolution pyramid, then like the actually you can think of the shape is smaller because in the lower resolution, like the pixel is much bigger than it's like corresponding to a smaller shape in terms of like pixel unit. So then a simple refinement of the optical flow approach will be like we just take the pyramid. So then like we will just like uh, do the shift like or find the optical flow in the highest level or the lowest resolution first, and then you propagate that. Like basically you find the shift in here, then you warp like one of the image so that make the shift here now the in the next level is smaller. So then like we can like find the optical flow again, and then you warp and kind of like I mean for this one and so on and so forth. So this will be the result without like doing this pyramid. As you can see, like for this is like actually the results right for the scene we just showed earlier. You have the tree here, oops, and the tree is like you can see like it's not doing well for the kind of like the pixel inside here, right? So because the motion is too big or so on. But if we have pyramid, then it's doing much better basically. Um, and okay, this we actually I forgot to move this to application, but anyway, so so this is just one application like uh that we can use optical flow to do like motion segmentation. Um, for example, if you think of like have different objects, right? So you can just group object have the same motion together, or like I should say the pixels with same motion together, and that pixels will should correspond to the same object. So it's a very simple like kind of idea. So for example, like this is the result if you we're trying to group like kind of like pixels that have the similar motions. Then like it's pretty nicely like segment like this tree here from the background here, and this is a closer and farther background here. So this is a little bit detail, like um, yeah, actually, you this is using a fine motion, but you can of course use other motion as well. For example, like I can do a homography, like have more parameters. That's fine with that also. So, but let's say if you use a fine motion here, so we assume that like U and V will take this kind of like representation here. So then I can replace U and V by this guy, right? Uh, and then like then we are trying to solve this A, B, and sorry, like A1, A2, and so on, like this coefficients here. So again, I is trying to solve this square problem. So we have like different pixels, we have same A, and so on, right? So we'll just say for we can, for example, take again like Lucas candidate, we can take the windows, for example, 5 by 5, and then each of them will have the same, we'll assume to have same A1, A2, and so on. And then we have like, again, 25 equations, but only have 6 unknown, then we can solve this. And then afterward, we can just group them together. So we have like, for example, these are the A and B that, sorry, like A1 to A6 that have the similar uh, kind of like mm, um, similar values because they have the same motion, right? You expect that they have like the values are kind of like close to one another. So, and then you can cluster together, and this guy probably is like pretty far away, so that is correspond to another cluster. And that's the orange one still like maybe another cluster. Then when you group all these cluster together, then you have the motion segmentation. Um, yeah. So this is some results showing here. Um, and uh, And yeah, as I said, I probably should move that one to this application here. And, and this is some other illustration of application. For example, like you can use optical flow. That's like a pre-processing step to get the correspondence of, to get a dense correspondence, and can use that to estimate 3D structure. So, and um, and this is uh, a very similar application. Like you do the motion segmentation, but more precisely, maybe we want to segment the foreground from the background. So we have like someone is moving, and then like maybe like we want to just get that someone rather than like kind of like cutter by the background. Um, and that's basically what we talked about earlier. We can do motion segmentation. And we can, of course, I can use that to track objects. So we will talk more about tracking like next time. So, but apparently, like you already can use like optical flow for tracking, and and basically like you can, for example, you can start with like uh, for example, like if I can just simply like put a, for example, I like to track this car here. I may just put a square here, and then I try to track the points inside this square here, and then um you yeah, continue to update and so on. And this is another example trying to track like not just a rigid object, but maybe like a object like, for example, more kind of morphable object, like for example, like for a person, and then you can check like individual component, like parts of the person, so and then find the pose and so on. So this is like a summary, like for optical flow, like we we talk about like the three assumptions there. Like the small motion can kind of like get away with that, like with, for example, like pyramid to some extent. And we have the brightness constancy assumption. That one probably we cannot. If, for example, like if you have a TV like in the scene, you can never tell like at this low level like whether it's like the TV itself is moving, or like this TV is on a truck, that is like moving, or like on a trolley is like moving, or like the scene in the TV is like inside is like moving, right? There's no way you can like figure that out like using optical folder alone. Um, and what's the third assumption? Like brightness constancy is more. Uh, I have horrible memory. Okay. Anyway, so yeah, I guess that's it. So maybe I should really take a look. So yeah, spatial coherence. So we are assuming like mostly like all the points are moving in the same motion. So okay, I think that, oh, okay, actually I have quite a lot more time than I expected. So but let's see, like I guess maybe I will do a little bit demo or something like uh so uh let's see if I can find, where's my code here. Oh yeah. So this is a several demo that like, let's say we have let me just run it first and then I can explain it maybe. Yeah. Where's that? Oh yeah, okay. So this is an example. I just say extract from open Siri. So um this is a scene that like you have maybe I start from the beginning again. Is so it first I look for several points that is easy to track, and then it's trying to track those points. So and it's like kind of like drawing all the trajectory as well. So uh you can still like, okay, like you're trying to track this couple person here. Oh, okay, what, why is I hmm, I don't know why the kernel will restart. So anyway, so we can take a quick look of the code. I guess um there's some parameter for the corner detector. So it's trying to uh extract good features. So here like I have load the videos here. So the is it that kernel here? Let me, okay, now should be fine. So um yeah, for some reason it's quite slow. I don't know why. So here you can ignore that it's just some visualization thing. So main thing is that like I read the image, right, and then read the frame, and this convert to like grayscale. This we use this OpenCV command here to get the good feature to track them, and there's some parameters we put in earlier. There's like the number of corners, the quality level, and so on. So this one you probably need to look at the API for detail. So but this is like quite interpretable. For example, maximum corners, the quality level. I assume the quality level is like should, let's say if I decrease it, like I get more point or like fewer point. Let's see. Yeah, if I decrease the quality level, I will get more points here to track. So they will be less robust. Like here, like it's essentially just using like Harris corner detector. If you remember, but for the Harris corner detector, that's the M matrix. I don't know, like if I yeah, you remember it's like basically this matrix here. If if you have I don't know whether I should ask it again. So but this is something good to know and memorize. Maybe I will ask again. So I just ask like let's see if I can. So for this matrix here, this A transpose A here, do you remember like if it's a corner, so I have like if I find the eigenvalue is a lambda one, lambda two of this one, of this this is the eigenvalue of this guy here. Lambda two. So corner, if like maybe I give a couple options here, lambda one, lambda two, both bigger than zero, lambda one, lambda two approximately equal to zero, lambda one bigger 0, lambda two approximately equal to 0. So option A, B, and C. So which one is likely to, which one is a corner? Oh yeah, you guys probably get um yeah. So this is a good picture kind of remember. Like this show up like several times in comparisons. Like um that matrix, like if you remember the Hertz current detector, this is like something like very convenient to check like what's the local kind of like characteristics or like of that object. So um and so yeah. So I guess that's fine. But yeah, it's good to know. I would say like good to remember, have an idea for that one. So and okay, let me get back to the code here. Yes, we mentioned this quality level. And so this is really using the highest corner detector. So if I decrease this level, most likely just like make it basically it's like maybe I should copy this thing here also. It's easier. Oh, okay. I cannot copy that. That's surprising. Let me try again. Oh, okay, I see. So the quality level basically just change like the threshold here. So if you remember, like in Harris corner detector, you kind of like trying to do something like have a funny equation that is a I now I can't forget also like I think it's a um the determinant minus lambda 1 plus lambda 2 square, something like that. That will deter that will decide whether that if that value is big, um, then it's likely to okay, yeah. Let me don't write it because I mostly will make a mistake because my memory is not that great. But the idea is just like if you have a smaller quality value, then the threshold actually why shouldn't just even ask you guys like so maybe just A/B question. So if I decrease this quality level here, so as I did like earlier, so I did that like from let's say this is option A and option B. I did that like quality level like from 0.3 to 0.01. So it should be A or B. Is my question clear? So I have this uh, quality level parameter in doing this good feature to track command here. And in the quality level, like if I make it smaller for the quality level, like from 0.3 to 0.01, do you think it should be like case A, basically my threshold like moving in this direction? Or like when I say this direction, I say the threshold starting from here to here. This is case A. Or like case B would be like my threshold from here move to let's say here. Yeah, I guess this time like most of you guys are correct. So um know that like if I decrease this quality level, as you can see, like I get more points here, right? And everything like on this side of this boundary or this side of this yeah on this side of this boundary is considered corner or like good feature to track. So therefore when I decrease that actually I'm moving this uh moving my kind of like threshold here like to towards more the origin. So okay, so that's the parameter for the corner detector or like whatever good feature to track. So then like this is also just visualization. We create mask here. The mask here is just to put in the trajectory here. Like so you see that like each time it basically draw on the mask and then put the mask say add the mask to the frame. So like we kind of like visualizing the image instead of just the frame or the mask. And then like the main command is pretty simple, like because we just directly call OpenCV command. We do an optical flow. This is using the Lucas Canada. Um, for Lucas Canada here, like in the OpenCV implementation, is assuming a let's see. I actually is in general is considered a sparse optical flow. So OLED you can of course use it densely also. You basically need to put in what point you want to track. So of course I can track all every points in the screen. For example, like I can um let's see. I'm not sure. I want to try that. Let me see if I can change it easy and try that. What's PCO here? So PCO, it looks like, oh, why is it there's a 1, 2 here? Okay, I guess it's just um I don't know if I do something like that, maybe I will screw things up. I'll try like 2 minutes. If it works, it works. If it doesn't, then let's see. I have this. What's the size of the image here? 360, 640. My biggest problem is always I can't figure out which one is which. So I have 360 and 640. Yeah, if I check every point, probably it's very ugly. Let's see if I check every other point, maybe. Yeah, if I do something like that, probably I won't have enough time. Let's see, maybe 5. Oh, maybe 10. Why should? Oh, okay. I'm not really doing things correctly. I should here divide by 10 maybe. And then outside maybe multiplied by 10. And then I see P1, maybe I call P1. No, probably not yet. I call it X, X, Y, Y. Let's see what do I get. Yeah, I need to make it integer. Let's just. So this is to 6 feet. Let's see. This is X, this is Y. Let's see. And see, I think that's fine. Okay, I guess I'm getting close. Let's look at that again. Let's see, maybe I call this P1. I need to add another dimension. Let's see. Or maybe maybe I just do that. Like probably hopefully it's okay. Yeah, don't do like I do now. I just hard coding everything because of time. Let's see. Let me code P2 level. Okay. It looks okay. Let's try that. So let's see if I have a PCO here. There's a P1. Oh, it is trying to select good points also. Like I probably will crash this entire thing, honestly. Let's see, P1. Does it have a P2 here? Let's see. It's good. Doesn't have P2, PCO. Let's call, let's say like PCO equal to P2, just overwrite this. And that's a PCO. I have P1 here. P1, PCO. Okay, I don't think it changed PCO afterward. Oh, okay. Let's see. PCO, good new shape. Where's good new shape? Oh, good new. Okay, good new reshape. Yeah, that's fine. Okay, let's try that. I don't know how bad is that. Maybe it will crash. Why is not showing all the points? Yeah, it has to do with the. Let me. Yeah, I hope this okay. This I should I want to what should I say, like you see, like when I have this kind of problem, maybe I should pause a little bit. I have this problem. This occurred like a lot, like when you play with OpenCL like this, like because I unlike MATLAB is very sensitive with the, I mean Python is sensitive to your data types. So so for example, like here in OpenCV, like I got problem because my type is like flow here. I should make it integer. So let me just yeah, actually I can comment this one here. P2 was that 32 or 64? I forgot. My super bad memory is horrible. 64. Oh, okay, not 64. I should have like 432. 432. Okay, I don't think I have enough time to fix this kind of bug. So unfortunately, I'll give up this one here. So maybe I just show you this another one demo, just a slight modification. Wait a sec. Why is? Oh yeah. So this is the one with my camera here. So it's also like checking only a few points, right? So maybe I start this again. Oops, but whenever I use the mouse, it okay. Oops. But I guess like something interesting is like if I play with the pawns here. So let's say if I move to let's see, maybe this one, something like. So I let's see. I try to move this purple point here. You see the kind of like the the kind of constraint or like the limitation of optical flow is like it cannot track because I on the edge, like remember, like that's exactly the problem. Like if your point is like not on a corner or something that like it cannot be tracked uh easily. Like you cannot basically you cannot be sure like when it's on the edge, then whether the point is like okay, anyway, I'm really out of time. Maybe I will repeat a little bit next time. Oh, okay. By the way, like of course remember to for your homework and also uh next Tuesday, I believe is an instruction holiday, so there will be no class. We'll have a class. Oh, wait a sec. Link to submit the survey. Uh, oh, uh, let me take a look. So, let me take a look quickly. Uh, let me, I guess maybe by default it doesn't allow you. So let me just, okay, say for the one for 25th, I guess let me just go here. Uh, big. Yeah, I guess it's this one. Let me just allow multiple attend. Okay, I guess that should work. Yeah, you may want to try again. It should work now. So, oh, okay. I only changed this one. I assume that you only need to resubmit for this one, right? You probably won't need to resubmit for the other one. So, but let me know if you have any kind of like, yeah. So, okay, good. So, again, there will be no class next Tuesday. So I will see you guys on Thursday. So, okay.
Thank you.
Thanks.